7.6 concerns itself with this law, which is known as the, what is it, the Ernst equation? I just had it. Boo, 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 boo. No, it's just another rewrite of the Gibbs free energy equation, sorry. And it's based on the Faraday constant, which is expressed up here, 96,500 coulombs per mole of electrons. So you have to know that constant. Um, but it's another way of calculating the Gibbs free energy. Now keep in mind, if this comes out as negative, you're going to have a spontaneous reaction. Also, if E naught comes out as positive, you're going to have a spontaneous reaction. So that's what this chapter is all about. You also need to know this table here. It's related to whether it's spontaneous at equilibrium or not. It's related to K. So when K's products and reactants are totally balanced, you have equilibrium. When K is bigger than 1, there's more products than reactants, you're going to have a spontaneous. When there's more reactants than products, you're generally going to have non-spontaneous. One thing we've come across is amperage. So amperage is coulombs per second. So for instance, 15 amps is 15 coulombs per second. We're going to need this to convert Faraday's constants to come up with how many moles, for instance, because Faraday, like all constants, they can be flipped. It's 96,500 coulombs per 1 mole of electrons, or it's 1 mole of electrons per 96,500 coulombs. We're going to get that as well. Now, technically, we don't even need this item from the page because it's obvious. To turn Cr3 plus into solid, we need 3 electrons. And you can tell it's 3 plus here. So really, this is the only information we need. And we can see that for every solid chromium we produce, there's 3 electrons. So the relationship is for every 1 mole of Cr3 plus, there's 3 moles of electrons. And since Faraday's law is about 96,500 coulombs for every 1 mole of electrons, it's quite clear that we have to reverse that for every 96,500. So that's our first step, is figuring out how many moles, coulombs, there we go. Now we'll want to cancel out our coulombs, won't we? Well, we happen to know that we're using this many coulombs. So that means the coulombs will cancel, the moles of electrons will cancel, and we'll just be left with moles of Cr3 plus. So this is the formula we would use, is 1 mole of Cr3 plus for every 3 moles of electrons. We know, thanks to Faraday's constant, that for every 1 mole of electron, there's 96,500 coulombs is required, and we know it's this. So coulombs are going to cancel, moles of electrons are going to cancel, and I'm going to be left with moles of that, which makes perfect sense. So it's essentially a ratio of these coulombs and a ratio of these moles. So it's a third times whatever that ratio is. It's clearly going to be much less than 1. So take out our calculator. 1 divided by 3 times 2475 and divided by 96,500. And I should always make sure I'm using the right constant at this time of night. Yeah, 96,500. And I get this many moles. Very tiny. Write it down. And I don't need all of it. And now I have to look up the atomic mass of this. Well, atomic mass of chromium is, that's how many grams there is per mole. And it's clear that the question is asking me how many grams do I need. So I want to end up with the words grams. So this rounds up to 52 grams per mole. And it's clear I have this many moles. I want the word moles to cancel out. This is also moles of CR3 down here. These will cancel. And so that means if I take the ratio I have in the calculator and multiply it by the mass, I get the number of grams that are added. Then I have to go back and look at my question and realize I'm 2 sig figs, which means this how many grams of chromium will be added in that space of time at that amperage, which turns out to be correct, which is good. So all these questions will use a variation of that. So what they ask for is time. They give us mass, so we should look up atomic mass of nickel. We know it's 2 electrons, we know how many coulombs per second, and we know Faraday's constant. So we should look up the atomic mass of nickel. So there's the atomic mass of nickel. So we need to figure out how many moles this is, obviously. Since it's 58.7 grams per mole, we want to end up with the word moles. It's 1 mole of 58.7 grams. And we have learned this many times, that it's simply mass divided by atomic mass to get our moles. So clearly I'm going to have slightly more than 2 moles. So now I know that I have this many moles. I have this many electrons. And I'm looking for the unit time. Well, I can see that time is there. So I should probably flip that. There's 1 second for 0.5 coulombs. And I also now know I want to cancel coulombs. Well, Faraday's constant is 96,500 coulombs per mole of electrons. So that means I want to cancel electrons. And over here, I can see that there's 2 electrons, or moles of electrons, for every 1 mole of nickel ion. That's what this equation tells us. Which means if I use this, I need to cancel out the word moles of nickel ion. All these things are multiplying each other. And lo and behold, there I have moles of nickel ion right there. Just going to do it like this. So that means if this is done, here's what cancels. This should be moles of electrons, by the way. And I'll be left with seconds. That's how you use your units. That means I have to take 2.12 times it by 2, because for every 1 mole of nickel, there's 2 moles of electrons. I have to multiply this by figuring out how many coulombs, and then I have to use this ratio to figure out how long, and if you look carefully, it's twice as long. So if I took a guess, this is going to come out 4. This is going to come out about 200,000. So it's going to be about 800,000. And so it's going to be quite a while. So if I'm going to guess really quickly, my answer is going to be that many seconds, that many minutes, that many hours, that many days. And you can break it down. Let's see if I'm close. I think I'm right. So we'll go back to our calculator. Should still have the moles in there. Oh, I erased it. Doesn't matter. 2.19471 is good enough. Times 2. There's 96,500. And don't forget we have to divide it by 0.5. Sure enough, that's 800. That many seconds are pretty good. Let's hope I'm right. Oh, I didn't read the last part. Look at that. You got to read the whole question. So this is how long. This is how long for 1 screw. So I got to read the question carefully. And if you look carefully, they tell us $32 screws. It's sneaky. So I then have to multiply this by 32. Let's come up with my seconds answers first. That many seconds? I don't know about that. 0.5 amps, 32 screws required for each screw. Each screw? Okay. Yeah, looks like it might be right. Divide that by. It seems so ridiculous though. That many minutes. The hours. What the answer is going to be. I probably should just look it up instead of this. Yeah, it seems like I'm off somehow. Yeah, but then numbers don't seem wrong though. So many hours, how many days. Okay, they're looking at that. So if you look at this and you want to figure out days, you didn't catch it all. Or sorry, if this is the number of days and you want to figure out, well, how many hours after that 304th day, you take this fraction here, subtract 304, and you multiply by, well, how many hours in a day? 24. It's going to take 10 hours. And then if you want to convert that, the next part, that's 3. This so far is days, 10 hours. You want to convert this next part to minutes. Subtract the 10. There's 60 minutes in an hour. It's this many minutes. And then you take the last part and multiply it by 60 to get the seconds. There you go. I think if I'm going to guess, instead your book said, since there's 2 sig figs, it probably just said 300 days. Let's have a look. Let's hope I'm not way off. Oh yeah, I'm way off. So there's some calculation errors going on here. So, but that's the basic idea of how to do it. So I'll go figure out where my calculation mistake was and come back and do it. Does seem like it'd be ridiculous, but I think maybe they're looking at one screw. Oh, found my problem. Sorry. This fatigue. Milligrams. So my answer probably should have been divided by 1,000, but I'll verify the math here. Yeah, so this is the equation here. So yeah, I just had to divide it by 1,000. Right here, this one had to be divided by 1,000, I think. So it's 2 times this, because you want the moles of nickel to cancel out, the moles of electron to cancel out, you want the coulombs to cancel out, and you're left with seconds. Then you have to multiply it by 32 screws. And here's what we get. So this is how many seconds. Maybe did I get that wrong? 96. Let's try that. It doesn't seem right here. 200,000. Drop it by 200, 400, 800. Yeah, that's wrong. So it's this 0.002 2947 and hit equals. Yeah, times 96,500. equals. We hit divided by 0.5, that should double. Yeah, okay, one screw should take that many seconds. And 32 screws should take that many seconds. I think they forgot to multiply by 32. Hang on. That many seconds. This is for one screw. And I think technically it should have come out as 820 seconds, but times 32. This many for 32 screws. So we'll just have that, and it should be this many seconds for one screw. And I think actually technically this many for 32 screws, but we're just going to use the full thing. In terms of hours, I'm just going to do that. There we go. And see which one they used. That's how many seconds. That's how many minutes. That's how many hours. So if we're doing hours, it should be that many hours for 32 screws. And if we're doing seconds, it should be 26,000 seconds for 32 screws. Yeah, see, they've screwed it up here. That's per screw, and that's for 32 screws. So at least our second calculation was correct. So this thing's the same thing, just this time they've left out the current. Exact same process. So we have to figure out the amount of coulombs. Now a little trick to here is Ag is almost 1 plus. Almost always 1 plus. So it's going to take 1 electron. So it's going to be a 1-to-1 ratio, which is something they left out of this question. But first we have to figure out how many moles is 12 grams. We figure out it's 0.1112 moles of Ag using the atomic mass of 107.9. We come up with that many moles. Now we have to convert that. We know there's 1 moles of electrons for every moles of Ag. We know that there's 96,500 coulombs for every 1 mole of electron. So we have to figure out how many coulombs before we can figure out amperage, because it's coulombs per second. So when we take that, we get this many coulombs. So that's how many coulombs we need, or are required. Now we need to figure out how many seconds is 1.5 hours. So we have to multiply by 60 minutes per every 1 hour. And then we have to multiply by 60 seconds for every 1 minute. And this way the words hours cancel out. And words minutes cancel, and we're left with 6 with S, seconds. I know 60 times 60 is 3,600, so times 1.5 will be 4,800, I believe. Oh, way off. That's right, because it's 1,800 plus 36. There we go. So it's this many seconds. So since the amperage is simply coulombs divided by seconds, we just take the coulombs we discovered and we divide it by that many seconds. Just clear this. And we get this. This is our amperage. Then we have to look at our question and see that we're dealing with 3. So there you go. That's our answer, 1.199. And that's the correct answer. Thank goodness, no calculation errors. Here's where you need your units. So if I look carefully at this question, they want to know the mass. Well, there's the atomic mass of cobalt. So here's grams per mole. So clearly I want to get rid of moles. Well, they tell you that it's COF2, so it's CO2 plus to 2 electrons to get to a solid. That means there's 1 mole of CO for 2 moles of electrons. I know it, I have to use this ratio to get rid of the words moles of CO. It means I need to get rid of the moles of E minus. Well, I know the Faraday's law, so there's 1 mole of electrons for every 96,500 coulombs there. And I've calculated the coulombs here, so I have to multiply this whole thing by coulombs to get rid of the word coulombs, which means I take my atomic mass, I divide it by 2, I divide it by 96,500, and I multiply it by this, and I get this. This is the number of grams that I successfully collect. And I have to go to 3. Correct. What volume of oxygen gas evolves at the other electrode? Determine the volume at STP. That's tough. Determine the volume at STP. So for this one, it's not as tough as it looks. You have to go to this equation, which is the closest H2O to CO2 plus, in which they pretty much tell you oxygen is derived, which tells you the water is being hydrolyzed. And because it's a half mole, I multiplied everything by 2 just to make it easier, of 1 mole of O2 for 4 electrons, so that we get this ratio. Because if you remember from standard, 22.4 liters of any gas is created for every 1 mole, no matter what the gas is. So really I just need the moles of oxygen. Well, I know 1 mole of oxygen for every 4 electrons. I know that there's 1 mole of electrons for every 96,500 coulombs thanks to Faraday's law. The electrons will come out. I know the amount of coulombs we calculated out here, so the coulombs come out, and I'll be left with moles of oxygen. So I take 17,640 divided by 96,500 and divide by 4, and I get, then I have to take whatever, here I'll do it before, multiplied by 20.4. This is how many moles of O2 you have, and then you have to multiply it by the constant, and it's this, it's the answer. And then you have to, again, 3 sig figs. And that's correct. In terms of chemical tests to determine the gas is indeed oxygen, I'll leave that up to you. You can't use a flame because a flame will ignite both H plus and oxygen. You could see if it reacts a certain way. You could look at the color of the flame. The color of hydrogen will be different than oxygen. You certainly wouldn't want to breathe it. What else could you do? Oh, hydrogen's lighter. You could fill a balloon with it. Since only 2 gases can be produced, hydrogen would float and oxygen would not. There's probably better tests than all of that. Let's see what the book says. Yeah. Relighting a glowing splint. Yeah, that's technically not a good idea. Using an indicator show the accompanying H plus. Yeah, because there will be H plus being produced. Yeah. You're just showing that if there's H plus, there's O2 because it's water. I don't like either of those answers. This is a stupid question. So for this answer, any reaction where the E naught is positive or the Gibbs naught is negative will be spontaneous. This one's a little tricky, actually. You have to use your knowledge of reduction and oxidation to realize that H2 here goes from 1 plus to 0, which means it gained electrons, and O went from 2 minus to 0, which means it lost electrons. So you start by saying, okay, so how did I come up with these? Because it's complicated with water. I should really have taught you this. I don't think they ever did. You start with the water on the left, and you can use both of them. It doesn't really matter. It'll balance out. And then on the right, you say, I've come up with gas here. So the first thing you have to do is balance out the oxygen with water. I can see that there's 2 oxygens, so I have to come up with 2 waters. Just stick with me. This will make sense in a second. And then I'm going to have to say, well, wait a minute. I've created 4 extra hydrogens, so I have to balance it out with 4 extra hydrogens. And then I said, well, wait a minute. I've created 4+ charges on the left. So I've got to add 4 electrons on the left. And I'll say, wait a minute, I got 2 waters on the right and 2 waters on the left. And I'll say, wait a minute, everything's divisible by 2. And you get to that equation. Well, when you look that up on the reduction potential table, you see it's the neutral one. It's 0 volts. And then you do the same thing with the water. Well, I got water. Doesn't matter if you use the 2. It becomes O2, gas. And you say, well, wait a minute. Okay, I got 2 oxygens, I'm fine. But I can see I've got 4 hydrogens over there. So I'm going to add 4 hydrogens. Now I'm going to say, well, I've got too many plus charges on the right. So I'm going to add 4 electrons. And it's liquid on the right, of course. And then I get this. And I say, okay, that's oxygen releasing things. And you might not be able to find that on the table because they do this strange thing that I don't quite agree with. They half everything. Like that. And then you can say, okay, I can see it on the table here. It's in this direction. Here, I'll show it to you. It's right here. But you can see that it's in the wrong direction. So to get it into this direction, I have to take this charge and make it negative. Now, as soon as you see a negative charge and we add it to the 0, obviously, this is going to be the voltage potential. So right away we can say that's a negative. It's not spontaneous. Then you can use the G formula, which is the number of electrons times the constant. Oh, I got the wrong number there. Times that. And you can see a negative times a negative is going to come out positive, and your Gibson's free energy is positive, which should tell you that the positive Gibbs free energy is not going to produce a spontaneous reaction. I think I might have gotten this calculation wrong. I've got to divide it by 1,000 because that answer's in joules. And we need it in kilojoules. Oh, then it should be 2.7. I got that wrong too. Should be this kilojoules. And then if I look up, geez, good question what the answer should be. Should just be 237 kilojoules, but I think I might have gotten that number wrong. Yes, I did. So the mistake I made here was converting my reaction that I balanced nicely into half mole, whereas these are per moles, so I can't use the half mole. So I should have left it in the original like this. And then use that 4 electrons over here. And then divide by 1,000, and I guess they round up. I don't know how they came up with the rounding. But that is the correct answer, and it's not spontaneous because the Gibbs is positive and the E naught is negative. So next one will be similar. So in this one, you can see the hydrogen over here, which is normally 1 plus, is still 1 plus. And over here is 1 plus, so the hydrogen didn't change. But oxygen went from 0 to 2 minus, so it gained 2 electrons. And iron went from solid to 2 plus, so it lost 2 electrons. And here's how you balance that. This question puzzles me because I got it and I've seen it before. And then when I checked your book, it's got a very strange answer. But it's the standard thing that we just did. So first of all, you've got to look that iron is losing 2 electrons. Oxygen is gaining 2 electrons. You write first your iron to that, and all you have to do is add 4 electrons. And it matches the electric potential here, except you'd have to reverse it. It's the iron that is oxidizing, so it's positive 0.45. Over here, when you balance out the oxygen with the hydrogen, you discover mix 2 waters, you discover all your oxygen and hydrogen's already balanced, so you just have to balance out the charges by adding 4 here, which matches pretty much. They have it in half. You want to keep the 4 electrons because it's matching this one as well. And I know they've halved it here because they've lowered there's a you can see that they're all divisible by 2, so that's why they have it here. However, this has 4 electrons and this has 4 electrons, and that matches what's going on here. There are 4 electrons being transferred, and that's important for the Gibbs. But when I reverse this charge and keep this normal, I have an electric potential of 1.68 volts. I don't know how the book got 1.32, and I've done this one many times. This is indeed the volt potential. Now, when you create other substances that are common with rust, yes, that volt potential is not accurate. But the way they've written it, they have not included the other elements that are often associated with rust. And therefore, that's the only answer a student could come up with based on this formula. So I'm not sure what they're going for here. But anyway, the Gibbs free energy, by the way, since that's positive, it's spontaneous. And the Gibbs free energy will confirm that. It's negative 4 times the 96, 500 coulombs per electron. The electrons cancel out. Multiply by the voltage. And you get joules. It's going to come out positive because it's negative, because that's a negative and that's a positive, which further confirms that it's a spontaneous reaction. But you have to convert to kilojoules. So you take that and divide it by 1,000. And then you'd look up, but there's no real units. So we just go with that. Now, obviously the answer in the book's wrong because they have a different voltage, and I don't agree with their voltage. Their voltage is more the standard that indeed rust would happen. It's pretty close. Rust is really 1.2, but it's not 1.27. And I'm not sure how they got that. And then their Gibbs free energy is based on that. If you use that voltage, you'll get that. Anyway, the answer is it's spontaneous, but please ask your teacher how they got that voltage.